right, here's our video for characteristics of functions. We are starting our discussion by talking about increasing, decreasing, and constant intervals of a given graph. So we say that a graph is increasing when it goes up as it is followed from left to right. It's decreasing if it moves down as it is followed from left to right. So that might be a little confusing. So let's talk about why we're making this distinction. Let's say I have a parabola. You could look at this a certain way and say that from here to here it's increasing, and also from here to here it's increasing. So if I go on this side of the graph, I would be going from left to right. Like I'd be following my domain, my x values from left to right. As that happens, the y's are increasing. But from here, in order for the y's to be increasing, I would have to be following my x's from right to left, right? So as the x's go to the left, the y values are going up. So we have to distinguish one direction so that we're all having the same conversation about the behavior of the y's. So that's why it specifies from left to right. So in this case then, let me draw it again over here. When we specify that we're going from left to right, meaning the x's are going left to right and we're looking at what the y's are doing, then in this case, we say the graph is, the y values, the graph is decreasing on this section, right? Kind of like a roller coaster, you're going down. And then right here, it changes behavior and starts going up. So for this section, it's increasing, and for this section, it is decreasing. And that is what we mean by these definitions right here and why we're saying from left to right. And then if you have a graph that does not change as it is followed from left to right, so let's say we have this is a constant function, right? So let's say that was 4. The y values are constantly 4 as the x's are going from left to right. And that's what we mean by constant. So down here, we are going to identify the increasing, decreasing, and constant intervals. So for this first absolute value graph, it is increasing as x goes left to right. It is increasing from here, the y's are increasing there to there, and we want the domain for that section. So the left boundary there is at 2, and the right boundary is at 7. And you'll see that there's a closed circle here. So at the end of my increasing interval, I'm going to use a bracket. And the beginning of that, and I'm using interval notation, by the way, interval notation. And the beginning of that interval is at 2. But here's what's different about the 2. This point is shared by the increasing section and by the decreasing section. So I'm going to put a parenthesis here to imply that at the point of 2, the graph isn't increasing or decreasing at the actual 2. And that's only going to happen when 2 sections overlap at a value, because you'll notice at the 7 I put the bracket. So that's the end of the increasing interval. So then the decreasing interval, we want the domain for that section, starts here at the left, which is at -3, and it ends at 2. And then there's an open circle there at -3. So the decreasing interval is -3 to 2, parenthesis at -3 because of this open circle, parenthesis at 2 because at 2, these 2 sections are overlapping, so we're going to say it's neither increasing nor decreasing there. And there is no constant section, meaning there's no portion of the graph that looks like this. So I want you to pause. Well, actually, let me talk about number 2 first. So in this problem, there are multiple increasing and multiple decreasing sections. So remember, we're going from left to right on our domain. So think about it as a roller coaster that starts at the left. So if you're starting this roller coaster, air quotes, you're going down here. That's a decreasing section. Then you change direction and go up here. Then you begin decreasing again to here, and then you increase to here. So this first increasing section, here's my left and right boundary. You'll see that, I'm sorry, I might have said increasing, I meant decreasing. For this decreasing section, the left boundary is negative infinity, and the right boundary is at -3. So negative infinity to -3. Parenthesis at the -3 because it has two different sections overlapping on it. So we're going to say it's neither increasing nor decreasing. Then it increases. So I'm going to skip that one for a second. It starts decreasing again right here at -1. So at -1, it starts decreasing and it stops decreasing right there at 2. And because at -1 and 2, there's overlapping sections, we're going to use parentheses, and we're going to join those two intervals with a union. And then now I'm going to do my intervals for these two increasing sections, one here and one here. So the left boundary of this one is -3, and the right boundary is -1. And then there's a break, and then it picks up again here at 2. It ends at 4, and notice at 4, there's a closed circle and no other section overlapping with it, so it gets a bracket. And then there are no constant sections. Right? So I want you to take a minute and pause your video and try the last problem by yourself. Okay, here is my solutions to the last problem. I got real specific and did 1.5. If you rounded it to, 1 or 2, something super close, that would be okay. All right, on the back of the note sheet, I went ahead and did some annotating here. What we're going to talk about here are local min and local max. That word local means in a very specific area. It doesn't mean the minimum of the entire graph at all points. It doesn't necessarily mean the maximum of the entire graph at all points. It just means the minimum in a particular area and the maximum in a particular area. And in general, a local min and local max are called turning points. So a turning point is a point on the graph where the direction changes from increasing to decreasing or decreasing to increasing. So it's the point where the graph was going up, but now it's going down, and vice versa. When it changes from decreasing or going down to going up, increasing, we call that a local min. And when the other situation happens, changes from increasing to decreasing, we call it a local max. So I have this graph over here. It's not on your notes, so you might want to draw it in. There are 3 places where we have turning points: here, here, and here. So each of those are called a turning point. So we have 3 of those. So let's decide how many of those are local max. So that's where the turning point goes from increasing to decreasing. So, and remember, we're reading it from left to right. So here's where it's increasing to decreasing. So there's 1. And then here's increasing to decreasing. So there's 2. So there's 2 local max. That means this is a maximum for this area, and this is a maximum for this area of the graph. Not necessarily the whole graph, just in their areas between other turning points. And then this one here is a local min. That's going from decreasing to increasing. So as we go left to right, think about a roller coaster. It's decreasing here and then changes to increasing there. So we say that's a local min. So on these next few problems, we're going to identify local mins and maxes. On this problem right here, there's really only one turning point. It's right here. And the graph from left to right was decreasing and now it's increasing. So we're going to call that a local min, and we're going to identify it at its y value. The y value there is -2, so I'm going to say there's a local min value at -2. So y is -2. And there are no local maxes. You might feel like this and this are maximums, and they are maximum values for my range, but they're not what we would call a local max. It doesn't fit the definition. A local max is first of all, it's a turning point. These are not. This is an initial point and an ending point. They don't turn. It's where you're going from increasing to decreasing. This is not changing direction. This is not changing direction. It's not going from increasing to decreasing in either section. So we do not have any local maxes here. So take a minute, pause your video, and finish out number 2 and number 3. All right, here are my answers to those. Take a moment and compare yours to mine. For number 2, there are 2 mins at y equals -5 and y equals -7, and there's 1 max at y equals 0. And then for number 3, I'm going to start with the local max. There's a max at y equals 3. It goes from increasing to decreasing, so that fits our definition, but there are no mins. Now, it feels like there's a minimum value here and here, maybe even here. Now, those are minimum values as far as the range goes and for those particular areas, but they don't fit the definition of a local min, which says that a local min is a turning point that is changing from decreasing to increasing. So right here at this point, yes, it was decreasing first, but then it changed to a constant. It didn't change from decreasing to increasing at that point. And at this point, yes, it does change to increasing, but it's from a constant to an increasing, not from a decreasing section to an increasing section. So we would say no, that there are no local mins.